In this video, we're going to discuss two aspects of beam bending. The first, calculating the second moment of area, and the second, performing calculations on a problem that has an overhanging section of a beam. So to start talking about the second moment of area, we're going to focus on two different types of geometries. One, a rectangular cross-section, and the other, a circular cross-section. So a rectangular cross-section is kind of pretty straightforward in terms of what it looks like. It's just going to be a rectangle that's been extruded. So in many of your CAD practices or softwares, you're going to have examples where you make a little 2D rectangle and then you extrude it some distance. And so this aspect of calculating a second moment area is just looking at the rectangular cross section. And when we have that rectangular cross section, we'll say that we have a neutral axis like this, say in the z direction, and we have a height above that neutral axis we'll call y. And um, when we have this cross section, we're going to give it an overall height h. So this is not to be confused with what we've been discussing as c, right, which is usually given as the maximum distance from the neutral axis to the outer or the upper or bottom portion of the rectangle. B is the width. So when we start looking at performing this integral where we have the second moment of area as I, and we're doing the integral of y squared dA, what we need to think about is these bits of dAs, okay? And what we're going to do is essentially say that for this rectangular cross section, the bits of dAs, the small bits of airs, are going to be horizontal strips. So they're going to have a width dy, and they're going to go across this width like you see here. So dA will end up being b times dy, right? Because that's going to be the area in this strip. Now we've got a dA in terms of a dy, right? And we've got a y squared. So we can go ahead and perform this integral. And we're going to go from minus h over 2, right? So that's going to go from the bottom here, assuming that the neutral axis is halfway between the upper and the bottom surface. And we're going to go all the way up to h over 2, right? So up to this top surface. And y squared b dy. B we'll say is a constant, and we're going to have this then being equal to, well, b times 1/3 y cubed, and going from minus h over 2 to h over 2, and we plug the minus h over 2 and h over 2 into y, and we get bh cubed over 12. This is a pretty significantly famous formula. It turns out we do quite a bit with rectangular cross sections, and as you'll see in a little bit, we can also make use of this equation even if the cross section is not a solid rectangle. So you can imagine having examples where we have a removal or a hollow center, right? So often you see extruded rectangular hollow sections, and those can be calculated. What are those? The second moment of area, can be calculated by taking the outer calculation for I minus the inner calculation for I. We'll talk about that in a little bit. And as we mentioned a few minutes ago, we also are interested in looking at calculations for the second moment of area for a circular cross section. And so for that, here is a circle and it has radius c. And we can describe a w, okay, as being the length from, let's say, the y-axis to the um, outer portion, okay, along that y-axis, or along the z-axis, sorry. So at a y-axis along the z till it hits the outer surface, okay? So in this case, the dA will be 2w, so you know, there's a w going from here to here, times dy. So we're going to again take these y chunks. And we have the equation for a circle as being z squared plus y squared equals c squared. All right, well, you're probably more familiar with x squared plus y squared equals r squared. But this is the same thing, just that we have a y-axis and we have a z-axis instead of an x and a y-axis. So we can write out that z squared is going to be equal to c squared minus y squared, just rearranging that. And then we can say that w is equal to z, and we can plug that into here, and you see that we have a y squared term, we have a constant term, and so we can perform this integral on the dA, all right? So substituting this dA into the y squared dA, right? So going back in here, and so this is what we get. We get y squared times this dA, and when you perform this math out, what you get is that the second moment of area is equal to pi over 4 c to the fourth. Now, another way to look at this calculation is to uh, put our circular cross section in polar coordinates. And again, we're trying to calculate I equal to integral of y squared dA. And we have y equals r sine theta in this case. And so then dA, if you're calculating, you remember from your calc or multivariable calculus, you have that dA in polar coordinates can be r d theta. And we're going to do this integral, all right, of 0 to 2 pi, and then 0 to the radius, c, or c, right, that's over here. And we have r squared sine squared of theta times r d theta, right? So y plugged in there. And when you calculate this out, once again, you get that the second moment of area is pi over 4 c to the fourth. One thing you might be questioning is, why haven't I called this moment of inertia, right? Because it said second moment of area, or, uh, you know, uh, second moment of inertia, if you like, or moment of inertia. Well, inertia is often used with mass, right? The kind of the quintessential example, right, is F equals ma if you're dealing with linear motion, and so m is an inertia. Well, in these cases, we're actually performing this calculation on the dA. If the density is constant across these cross sections, which it often is when they're solid and made of one material, then we can kind of say, oh well, if I know what the density is, I can incorporate a mass in there, and I can calculate what the inertia will be. Okay, and so they end up being the same just by a scaling factor. But with these beams, we don't bring into this problem the mass of the object or the density of the object. This is an integral over the area only. Okay, but it's just something to keep in mind. Now, let's take a look at a cantilever beam with a rectangular cross section. And the question is, where is the bending stress the highest, and what is its magnitude? So before we had kind of talked about, okay, where is the bending strain or the normal strain going to be highest? And we also talked about in class how that is analogous to saying, okay, well, uh, sigma equals E epsilon for the uniaxial case, and so for normal loading on a bar. And so we can kind of see that if we're going to have a highest strain in a particular location, we're also going to have very likely very high normal stress at that same location. But now we can actually calculate that value, right? We had this, the flexure formula, sigma is equal to negative my over I, but we didn't really necessarily know how to calculate I. And now we just figured out how to, or now we've just discussed how to calculate I. So we can go ahead and look at this cantilevered beam and do a detailed analysis here. Once again, a good place to start with this problem, and you've now seen, and you've seen me kind of goof a little bit if you've been in class. this this creation of a shear force and bending moment diagram, or shear force and bending moment diagrams for this system. But we start by doing external equilibrium, and we calculate. I'll go through this quickly just because now we've done this multiple times. And we have our reaction moment, we have uh, our our reaction force R. We can look at the boundary conditions at the left side. We can look at the boundary conditions at the right side, and we can go ahead and we can draw the bending moment diagram, which looks like this. You know, if you look back at the notes, you see that it said minus PL instead of minus FL. And P and F, you know, just the variables that we use for the transverse concentrated force at the right end of this beam. So here is the bending moment diagram, and the equation for bending stress is going to be that sigma is equal to negative my over I. Well, where is the bending stress going to be maximum? There are, well, based on our discussion with uh, bending strain, you may already have this idea in your mind, but if not, let's just look at this equation. This quantity, all right, now we're talking the magnitude of this equation, is going to be greatest, right? The sigma is going to be greatest. The bending stress is going to be greatest when what? Well, when m is the most negative or the most positive, okay? And when y is large, all right? And when I is small. Now, this is a very important concept. I is completely dictated by the entire cross-sectional profile. Okay, so you don't, as you go to different locations along that beam, assuming the beam has a constant cross-section, it's not going to have an eye that is changing. Okay, so once you see the profile, lock it in. That's the I. Just like the J was, right? When we had the polar moment of inertia, or polar moment of area, okay, when we were doing torsion and twisting a rod. Or just like the cross-sectional area of a bar is a constant. You can't change that, okay? And what I mean by change, I mean we're looking at finding a maximum. So we're looking at, okay, maybe there could be varying m and y. So I'm not going to change what location I'm looking at, or I am going to change the location I'm looking at, but at all those locations I'm looking at, I is going to be constant. Okay, so we need to think about where are m and y going to be the largest values. Well, y is going to be the largest when we're out at the top or the bottom. Okay, so we can begin to think that sigma equals negative mc over I. That would be the largest, and so we're going to be interested in where this y equals c, which is equal to h over 2. Okay, so you can see the entire height there. And this is something, you know, this is a little bit tricky. You want to make sure that you realize, okay, it's half the height. You know, lots of us will make, including me, will make careless mistakes about what y should be plugged in here. Not h, but h over 2. And then the I we calculated previously on the past slide. We said it was bh cubed over 12. So now, okay, if we want the sigma max, we can type in, or we can substitute that we have FL times h over 2, and we have this all over bh cubed over 12. And so the maximum stress is going to be 6FL over BH squared. Okay. Um, so here is actually going back to the first class, and I'll talk about this probably more later, but if you go back to our first class where we introduced the scaling laws, we said that the maximum stress that a beam could, or the maximum, we actually just called it the maximum supportable load, right? And we said, hey, there's a load being hung on the end of the beam. We said, oh, it's going to be proportional to the thickness squared, okay? So the thicker I make it, the lower this can become, right? it's going to be proportional to the width of the beam squared, or the width of the beam, sorry, not squared, just b, the width. And it's going to go down as L increases, as the length increases. It goes with 1 over L. The strength will go up, right? And so you can see there's the L, there's the B, there's the H squared. And we can talk more about that, but I just wanted to point that out, that this equation that we just calculated is significant. And maybe I didn't say exactly where this is, okay, but we need to do so. That this sigma max, all right, is happening at the wall. All right, why? Because that's where we got the FL that we could plug in here. Okay? And it's happening at the top or the bottom surface. So in this case, right, this bottom portion right here, that is going to be under compression. So, if I circle that right there, and the top is going to be under tension. And that means that that's very likely, okay, where the beam will fail. And probably more likely, so I think either one of these would be fine. In many cases, we care, well, I should be careful. It depends a little bit on the material. Like if it were a brittle material, then often the compressive strength is higher than the tensile strength. So then you say, oh, it's probably going to fail on the top, right, for example. But this is where those values are going to be of equal magnitude. Now, let's talk a little bit about how to use, that's the second moment of area, the parallel axis theorem. And you probably are like, oh man, wow, it's a while since I talked about the parallel axis theorem. But in physics, you did discuss it, and here is a review that the second moment of area, okay, is equal to the summation of all the individual second moments of area that you might have in a system, plus the area of those individual second moments of area times the distance, okay, from the distance squared of each of those areas relative to some um, location or some axis. Okay, so if we think about an I-beam, and I guess I could have said, okay, right, this is the equation that we already have for a solid rectangle, ph cubed over 12. What do we think about with a solid, with an I-beam, sorry? We think that we might be able to describe it in terms of a few different rectangles. What are we talking about here? Well, where are the rectangles? The rectangles, and if I can calculate the eyes, and I know their distances from the axis that we're interested in using for a reference, then we can come up with the overall second moment of area without doing another complicated integral, right? The integral of y squared dA. We can essentially use addition, okay, and some kind of uh, more or less simple uh, algebraic expressions to figure out the overall um, second moment area. So where are the three rectangles? Okay, I guess I gave it away. There are three rectangles, right? So one of them is going to be in this uh, vertical, uh, or how should I say it, slender, tall, central region, okay? And that has width c, and it has a height of 2a, right? And so we can calculate this region's second moment of area just by using bh cubed over 12. And because we're going to do it around here. Okay, so that's one. Now look at this. There are two other rectangles that I can put on here, and if we look at it, this rectangle here. I can calculate a second moment of area for that region. Okay, and that one, the width, right, is going to be f, and this the naming's a little bit different, right? So right, this b and this b. are not quite um, the same, okay, because this b is going to be cubed, right? That's the thickness, right? So that goes into here, right? But that's just the, this is kind of, maybe I should have used a different parameter. I shouldn't have reused b, but you see the b up here is not the same as this b right here. And then we have our distance, okay, from the axis, the z-axis, to the centroid of our rectangle, right? So that can be given as a plus then half of this thickness for the top portion or the bottom portion. Okay, so that's a plus b over 2. So the algebra is a little bit messy, but I will still opine that this is a simpler way to do the calculations than trying to come up with kind of an interesting formula that's operating over different regions to do the integral of y squared dA, or multiple integrals, right? You could do integral from like minus a to a, and then minus quantity a plus b, right, to minus a, and then do another one, from a to b, right? But using the parallel axis theorem, what do we get? Well, one, we're going to say we're going to double, okay, whatever we get for the top, because this is going to be contributing the same amount at the bottom. And then using the parallel axis theorem and this portion of it, what we have is that we have the second moment of area for this kind of horizontal slender rectangle, and that's going to be the width times the thickness cubed over 12, and then we have it offset, all right, a distance that is going to be given by d squared, all right. So that's the distance from here to here, and the area is just BF, all right. So what is d squared, or what is d? D is this quantity of a plus b over 2, right, which we described previously. So we can now calculate the I for an I-beam, right, the second moment area for an I-beam using this parallel axis theorem. Now, what about a cantilevered beam with an applied moment? Right? So if we have this cross section, which is an I, as given here, and the web thickness is now given as W. All right, so we're kind of flipping around the parameters a little bit because we just had like a B and an F. All right, so it's a little bit tricky. What is the maximum bending stress is what we're going to be asking ourselves. Um, so how do we go about approaching this problem? Well, we have an applied moment here, and so the moment's going to be the same across the entire cross section, regardless of what the cross section. Sorry, the moment's going to be the same across the entire length of the beam, regardless of what the cross section might look like. And when we look at this equation, right, we have sigma equals, what is this equation? This is the flexure formula. And we already have this idea that sigma max is going to be when y is either at the top or the bottom of the beam, and it's not going to care too much. It's not going to care about its location along the length because m is constant. So how do we calculate I? Well, in this case, we can also think about taking an entire cross section like we have here and subtract this this region here and here, and this region in here and here, right? So that is another maybe simpler way of using the parallel axis theorem to be able to calculate out, because the d, when we say d, let me go back. The d is the distance to the centroid. So if the rectangles you're checking or you're selecting are have centroids that are on the z-axis, right, on the neutral axis, then you don't have to add this term. Okay, you just have to use the different second moment areas. But if, like in this case, the the centroid of these shapes is off axis from the z, from the neutral axis, then we have to use the di. Okay, so in this case, it's maybe even simpler to draw it out like this. Okay, so that we're subtracting away these two rectangles. They're smaller, okay, and we can give them dimensions, right? And they're the rectangles that would have been here, but they've been removed. Okay, so I can also be written as, for these geometries, bh cubed over 12 minus here the 2 times, because there are 2 of these, the dq cubed over 12. And in this case, the d, all right, which is not referring to the di that we have in the parallel axis theorem, that is going to be the b minus w over 2. And q is going to be equal to h minus 2w. So if we go through this calculation, we see that the sigma max is equal to 6 times this bending moment. That's constant across the entire beam. And we have the calculation of y, and we have calculation of these terms right here. Okay, y was the h over 2, and the I was this big equation over here. You know, in here, in this case, the maximum bending stress would be anywhere along the top or the bottom of the beam, right? And in the top is going to be in compression, and the bottom is going to be in tension. And this is not at a specified location like we had in the last problem, because the beam bending moment is constant along the length of the beam. Okay, now here is a temptation. Here is a tempting way to use the parallel axis theorem incorrectly. Let's say that we have this cross, as we see here, or this plus sign. We could be tempted to think of it as a rectangle and subtract away these 4 individual rectangles and just write it out as bh cubed over 12 minus 4 times the d cubed over 12. And we can substitute in our 2d plus w equals b for each or for this system. Okay, so what are we talking about? We're saying, okay, the 2d, right? 2 of these plus whatever the width, right, of that is going to be equal to b, and we can then say that d is equal to b minus w over 2. And we could calculate that out, and we can also say that 2q plus w is equal to h, and we can say that q is equal to h minus w over 2. So we could be tempted to do this. Why, though, is this not correct? Right? What are we doing correctly? Well, we haven't accounted for the centroids and their distances, the centroids of each of these 4 boxes, and their distance from the neutral axis, assuming, of course, that the neutral axis is going through this horizontal portion of the plus sign. So this analysis is not correct, and it's correctable. How it, is that a good thing to say? We could fix it, but we would need to uh, to make an accounting of their distances, okay, from the neutral axis. Now let's do it correctly, or one possibly correct way. Okay, we'll say that here we're going to make, and so the other way could have been corrected, right, if we had added the appropriate ADI terms. Here what we'll do is we'll say, okay, here's a horizontal, and then we don't have to do any DI business here, because the centroid of this shape is on the z-axis, on the neutral axis. we can add this vertical beam, okay? And again, that centroid is going to be on the neutral axis, right? So around here. But now we've double counted the overlapping region in the middle, so then we can subtract away this little box here, okay, in the middle, because when I stack these two on top of each other, I got twice of the central, the twice, you know what I'm talking about? I'm saying there's twice of this little block and this little block in here. So I got to subtract away that block. So to do that, or to do this entire integral, right, we just have bw cubed over 12. All right, that's this one. We'll have the w and well, I guess it's not b, but it's now h, right? They kind of flip, so we have h cubed here. And then we have this minus w to the fourth over 12, which is describing this cross section. So now we can say that the second moment of area is going to be equal to 1/12 times quantity bw cubed plus wh cubed minus w to the fourth. And this calculation is not that complicated. And it didn't involve us having to think much about the distance of the centroids of any of the shapes that we're using inside this system. We didn't have to think about that we did think about it, but the centroids were on the axis, the neutral axis. Okay, so this portion concludes what I wanted to talk about concerning the calculation of second moment of area. Now, let's go ahead and change things up a little bit and look at a problem, okay, that we have for question number 3 in the homework. All right, so here, what we're going to say is that there's a beam with an overhang, okay, and this overhang has a distributed force acting on it, and we're going to say that there's a square for the cross section. So this is kind of boring, right? Because if I know what if I know what the length is, now this length, all right, it says it has side length A, so this shouldn't be 10 millimeters, it should be A. Yeah, but you know, it could be on that order. 1 centimeter is not, you know, way off. And there's a point of analysis that is a distance y, all right, above the neutral axis. Okay, so this is also a little bit confusing. So we're going to say that, you know, this was the z axis, and this we're going to call the y, and we're going to say that this is a distance y above it. Okay. And we're saying that it's a distance d from the right end of the beam. So we are now going to the beam and we're saying that it is some spot, so maybe like about there. That's where we're interested in calculating out the bending stress. Okay. So how do we go about doing this problem? Let's break it down, and I'll try to do that. And sorry, I'm gonna now change my orientation of things here, and we'll see if we can do this in a kind of, there we go. Okay. So what we're going to look at is a cross section, or yes, we're already looking at a cross section, but we're going to look at a slice, better said, on the beam. And we're going to say that this is D from the free end. Okay, so this is a free end here. And we're going to perform our calculations for a moment about this region O. And we're going to say that the distributed load is still active here. Maybe I should I might need a little bit. Well, I think it'll be okay. We'll just do it like this. And if I use my convention, V will be positive and M will be positive with these orientations. This has magnitude W naught for the distributed force. So if we draw out now our another free body diagram, and maybe I'll try to make this one a little bit bigger, like this, then we have that there is an effective force acting at some W naught D, right? So I didn't use X here. I'm just using this variable D. I could have used like minus, I could have used like X1, X2, I could use some, but we're just using D here. Okay, and this is going to be acting at a distance. Okay, when I say D, this is the distance D. Okay, and this would be like the coordinate X or something like that, right? So this is that distance D. And this is going to be a length of D over 2. Okay. So V is again upward, and M is again acting like this. We need to figure out what the bending moment is at this sliced region. So to do that, we perform equilibrium. We're not going to use the differential integral forms here. We're just going to calculate the equilibrium. So we're going to have that summation of the forces in the y direction is going to be equal to 0. And we have a V that's acting positively, as we said prior, okay, here. And we have our minus W naught D, and that's going to be equal to 0. So now V is just going to be equal to W naught D. Summation for the moments at location O, which we called to be over here, that's going to be equal to 0. And we can say that we have a negative VD, okay, a minus M, okay, this is assuming that positive moment is coming out of the board, and we have a plus W naught D, okay, times D over 2. So we have W naught D, that's the force, and its distance that it's acting is D over 2. That's at the effective middle. And this is going to be equal to 0. So when we rearrange things, okay, we can calculate out what M is. So M is going to be equal to this quantity W naught. Okay, we had a D squared, we have a, yeah, let's see, we're going to have a D squared over 2. And then we had the V plugged in, right? So we have a, yeah, we're going to have a D squared over 2 minus D squared. And this is going to be equal to minus W naught D squared over 2. Okay. So how do we go about calculating the maximum bending stress? Well, we need to look at, okay, so I'm going to come over down here, sorry. Sigma max is going to be equal to minus my over I. And this is just a square cross section, so I is going to be the a to the 4th over 12, because that's essentially bh cubed over 12. But, you know, b and h are both equal to a. The y is going to be either up at the top or up at the bottom. So we'll say that y will be equal to plus or minus a over 2. And the, or I could have, if I want sigma max, you know, sometimes you might just write, instead of minus my over I, you just write mc, all right? And so this is, that's really c there, okay? And we calculate out what m is. M is going to be minus w naught d squared over 2. Okay, so with this, we can write out that the sigma max is going to be equal to w naught d squared over 2 times the a over 2 all over a to the 4th divided by 12. Okay, so this means that we're going to have 3, we're going to have an a, we're going to have, okay, so we're going to get a, whoop-de-doo, 3 omega naught d squared all over a cubed. I hope I didn't do any of the math wrong, because that part I was doing on the fly, right? But that's going to give us the max. If you look at this solution from 2015 for exam 2, it actually it's not a bad idea to look at it. You'll see that I went through the involved process of going from left to right and calculating the moment across the beam and then across the overhang as well. And that can be done, but this is an example where, in hindsight, the simpler way to look at solving this problem is going from the right, where there are no constraints on this free end, and we can, without too much difficulty, figure out how to calculate, like we did over here, just through equilibrium, the bending moment, the internal bending moment, and the internal shear force. Okay, I hope this example is helpful, and until the next time, thank you.